recognize. R equals A is a circle with the center at 0, 0 and a radius A, absolute value of A. If you have R equals something in the form 2A times sine of theta, that's going to be a circle. These are all circles, by the way. That's going to be a circle with a center at 0A and a radius of absolute value A. If you have R equals 2A times cosine theta, the center is A, 0, and the radius is absolute value A. Now, graphing polar equations takes a long time if you're doing it by hand. Luckily for us, we've got a calculator that will graph in polar form for us. So let me pull my calculator up. So here's what we're going to do. We're going to graph the equation R equals 1 plus sine of theta. First of all, you've got to switch the mode to polar mode. Oops. Wow. What are you doing? Which is the fourth line down where you can switch from function to parametric. The third option is polar. Now when you press y equals, you get R1, R2, R3, and we'll simply type in 1 plus sine of theta. Now you get theta the same way you get x when you're working with functions and t when you're working with parametrics. Now it's very important that your calculator be in radians. If your calculator for some reason is set in degrees, you're going to get weird and wacky things. Let's see. A good not parameter interval, but a good interval of values for theta would be 0 to 2 pi with a t-step or a theta step of pi over 24. That's what I've got right there. This actually is the viewing window that you get if you go with Zoom 4, which is the decimal viewing window. I really like that viewing window because it's square. You don't have to adjust it. And that's important for your polar graphs to have the right shape. If you pressed Zoom 6 in this particular case, first of all, that window is way bigger than you need. You don't need to be looking at -10 to +10 or x on x or y. So the decimal viewing window is a little bit better, and then you can always go in and just manually change your x mins and x maxes if the curve you see goes off the screen you're looking at. It's a good idea again to change the style of the graph to the ball and chain. It slows it down, and it's important sometimes to know how the graph is generated. You know, what direction is that curve sketched. So, you know, you'll have to play with it some and do some of these before you feel comfortable. Now, graph this equation. R is equal to 3 times the sine of 2 theta. And I would start with the viewing window that we've got here. Okay, so that curve, that equation generates a curve that looks kind of like a flower. That flower has 4 petals, one in the first quadrant, second quadrant, third quadrant, fourth quadrant. All right, now next question. In all of these graphs that we've looked at so far, whatever the starting point of the curve was, the graph came back That's really not what we just graphed. But, in each of these where we had the circle, our point started at the origin, looped around, and stopped at the origin. And then it sort of traced the same thing again. But our starting and stopping place was the same. With the sine of 2, with 1 plus sine of theta, we had something that looked kind of like that. Starting and stopping place was the same. With sine of 3 sine 2 theta, we had this. And honestly, I can't remember what order these petals were drawn in, but I think this is close. Started and stopped at the origin again. To get a complete graph, what we would consider a complete graph as far as a polar curve is concerned, is your starting place and your stopping place ought to be the same. So let's look at r is equal to the cosine of 2 theta over 5. So let me change my equation. Cosine of 2. What is the deal here? That's the deal. I need to switch back to math print. Okay. Now, y equals r is the cosine of the fraction. Daggum. Cosine of the fraction to theta over 5. So I'm going to start with the viewing window that I've looked at so far. And that's an interesting curve, but obviously we don't have a complete graph yet. And my window right now, if I can show it to you, is 0 to 2 pi. So 0 to 2 pi is not showing me everything I need to see. So what to do? Typically 0 to 2 pi works okay. In all the other examples we've looked at. So maybe what I need to look at is what value of theta will make 2 theta over 5 equivalent to 2 pi. So 2 theta equals 10 pi. Theta equals 5 pi. So maybe I should try that. So I'm going to change my theta maximum to 5, maybe 5, there we go, pi. And I'll hit graph. Okay, and we get more. That's not it yet. I want to change my style to the ball and chain to slow it down, make sure I can see everything that's happening. There we go. Almost. Goodness, that's a mess. Alright, I still don't quite have the right stuff. I'm also going to change my viewing window a little bit and blow this graph just up a little bit. Zoom in on it, in other words. Negative 2.35 to positive 2.35. I'll need a negative in that minimum. Negative. That's going to be better, I think, as far as me being able to see what is happening with that curve. So this is a really, really interesting graph. Alright, we don't have our starting point position location and our ending location being the same point. So really what needs to happen is that when theta is 0, then our value of r is cosine of 0. So r is 1. So that's the point 1, 0. And when theta is 2 pi, then we have r is equal to the cosine. No, excuse me, if theta is 5 pi, that was the last one I tried. Then r is equal to the cosine of 2 times 5 pi over 2. Do I have the right function? No. Over 5. Then we're looking at r is equal to the cosine of 2 pi. Cosine of 2 pi is 1 also. So that ordered pair is 1, 5 pi. Now the problem is these 2 points aren't in the same place. In general, we can kind of jump to what we need to do. The interval 0 to p that gives you a complete curve. There are a couple of things we have to think about. P is a multiple of the period of your function. And it's also a multiple of 2 pi. So the period of our function, for this equation, the period is 5 pi. So 0 to 5 pi was a good choice. Problem is 5 pi is not also a multiple of 2 pi. So I think I'm going to try 0 to 10 pi. Because that value needs to be a multiple of 2 pi and of the period of our function pi. So, giving it a try. And being very patient while it graphs and graphs and graphs. And your calculator will actually graph a little faster if you don't use the ball and chain. It's also harder to watch it and see what you're looking at. Alright, did you notice that the starting position and the stopping position of that graph were the same? That point right there. So 0 to 10 pi did it. You're always going to have your calculator to help you graph polar curves. You can think about, kind of do some guessing and checking. It's very, very easy to try something for the interval for your values of theta, and if it doesn't work, you try something else, and it's not a big deal.